and welcome back. In today's tutorial we will talk about LeNet 5. You have probably heard about LeNet 5 before because it is a fundamental convolutional neural network. We will see a bit of theory and also how to implement it using PyTorch. A little bit of history about LeNet 5. It was invented by Jan LeCun in 1998 and it was the first convolutional neural network. The first goal, or the main goal of this model, was to recognize handwritten digits. Now, the LeNet 5 architecture looks something like this, and it takes a 32 by 32 by 1 image that is grayscaled as input, and it outputs a prediction. Left to right, here the first layer we have a convolutional layer with 6 kernels of the size 5 times 5 and the stride of 1. Now these parameters, the kernel size basically defines the size of the convolutional filters, while the stride parameter is a integer value specifying the step of the convolution along the height and the width of the input. And this convolutional layer accepts this 32 by 32 image and it outputs a size 28 by 28 by 6. Now this goes into the average pooling layer, which has 6 kernels of size 2 by 2 and the stride of 2. The output of this layer is of size 14 by 14 by 6. After that comes another convolutional layer with the same configurations, just with 16 filters, and the output is 10 by 10 by 16. Then after that is again a pooling layer that is the same as this one here, just with 16 filters. This layer here will output a 5 by 5 by 16, and this goes into a fully connected layer, which then returns 120 units that go into the second fully connected layer that returns 84 units, and these 84 units go into a softmax function. This softmax function accepts these 84 units and it returns a vector of 10 values, each representing the probability of that image belonging to a specific class. Now that we know a bit of theory behind the LeNet 5 network, we can start building it. Here I have imported the necessary libraries like matplotlib, numpy, torch, torch vision, and etc. We will define a variable device which will store CPU or GPU depending on what we are training on. So I will run this, and if I print out the device, it will probably say that we are using a CUDA or GPU. In this step here, we will download the necessary dataset for the training and validation. I will not get in much detail here, I will just go through the code. If you want to learn more about data loaders, we covered this topic in a previous video. I will leave a link in the description below. Now, moving on, we will download the fashion MNIST dataset. We resize the images so that they are 32 by 32 and then convert them to tensors. This will automatically scale our images to the 0 to 1 range, and we also specify, this is important, the batch size to be 64. And we also shuffle our data. So we will run this. To get a better understanding of the data, we can extract one batch from the training set. So the training data will be enumerate of the train loader and batch index and images labels, so we'll extract them by using the next function on the training data. And then simply we will just print out images.shape and also labels.shape. And here it gives me an error, so train loader is not defined. Okay, I have placed a lower L here, so like this. And okay, we can see that we have 64 images that are of shape 1 times 32 by 32, and also we have 64 labels that correspond to these 64 images. And now comes the interesting stuff, building the LeNet 5 model. We will start by defining the class LeNet 5, and we will call nn.module, and then we will create a init function, so def init. Inside of here we'll pass in self. And after this we need to call super. This is the same as before, so pass in LeNet 5, the name of the class, also self, and call init. Okay, now the next step will be defining the layers. The easiest and most elegant way to create this model is by splitting the convolutional and linear layers. We can do this by creating two sequential models. One will be called convolutional layer and the second one a linear layer. And then here I'll call nn.sequential and also for the linear layer, like this. And then inside of the brackets here we will define the layers for the convolutional layer. So we will call nn.convolutional2d. After the convolutional layer we will specify the tan h activation function, then the average pooling layer, so average pool 2d. After this we will repeat it, so again the convolutional 2d, then the tan h, and again the average pool, like this. And then the last layer would be again a convolutional layer and again the tan h activation function. Now for the parameters, as we specified in the architecture above, the input channels will be 1, output channels will be 6, then the kernel size for the convolutional layer will be 5 by 5, so we specify 5 here, and also stride will be 1. I will copy these parameters because they are the same for each of these convolutional layers, like this. And now for the average pool layer, I'll specify the kernel size to be 2 by 2, so 2 here, the stride will be 2, and also I will set the padding to be 0, like this. I'll copy this and paste it here, and this way we created our convolutional layer. So here I have a typo, so convolutional layer. After the convolutional layer we can now start building the linear layer. So the linear layer will have two fully connected layers, so nn.linear, and the first activation function will also be a tan h, and then again a linear layer. I will specify the softmax activation function in the forward function directly, not here. So the parameters, the input will be 120, so input features 120, and output features will be 84. Here the input features will be 84 and the output features will be 10, like this. Now that we have our layers defined, we can now move on and create our forward function. So self and x will be the image. We first use the convolutional layer on that image. After that we need to flatten the result from the convolutional layers, so we'll call torch.flatten and we'll pass in that x and 1, like this. And then after this we can call the self.linear layer, pass it in the linear layer, the x, and then, as I mentioned before, I will use the f.softmax activation function on x, and the dimension I will set to be 1. And at the end I will just return that x. After we defined our model, we can now call it, so model will be the LeNet 5, and I will call to and pass in the device that we are going to use. So we'll use either GPU or CPU, and I will just print out the model. Okay, we have a typo, it's not tan, it's tan h, like this. Let's try again. Okay, we have another error, so it's not output features, it's out features, and hopefully we don't have any errors. Okay, here we can see our convolutional layer and also our linear layer. Okay, now that we have our model defined, the next step would be defining the optimizer and also the loss function. So for the optimizer we will use Adam. What are we going to optimize? We will optimize the model.parameters, and also the learning rate we will set to be 0.01, for example. And then the criterion will be nn.cross entropy loss, like this. Now we can train our models, so we will train it, for example, for 20 epochs, we will define two lists. One is for storing the training loss and the second one for the validation loss, like this. And then we do for epoch in range of the epochs. We will store the total training loss, we will set it to be 0, and also total validation loss will be 0. We specify that we will first train our model, so model.train, and we iterate through all of the batches. So for index, image label, in enumerate of the train loader. Now, first thing we need to do is send all of our images and labels to the device we are using. So image and label will be image to device and also label to device. After this, we can now zero the gradient, so optimizer.zeroGrad. After this, we do the for propagation, so model on the image, and then we calculate the loss, so criterion on the prediction and the true label. We then add to the total train loss the loss.item, like this, and we can now calculate the gradient, so loss.backward, and optimize the parameters, so optimizer.step. Okay, this is the step for the training. For the validation, here we will set it to be to model.eval, and we will define a total as 0, in which we will add every time our model guesses a class correctly. Then we will again iterate for index image label in enumerate. We will just now use the test loader, and here we also send the image and label to the device that we are using. After this, we do a forward propagation or a prediction, so model on that image, and we calculate the loss on the prediction and the true label, and we will store it into the total validation loss. Now we will do the prediction, so we will take out the softmax, so functional dot softmax of that prediction, dimension equals to 1. And then we will iterate through all of those predictions, so for I and P in enumerate of the prediction, we will check if the label of that I, of that image, is the same as torch.max of p.data of 0th and the first. So this part here will extract the maximum probability in the vector of 10 probabilities for each of the classes. And if this is the case, we will add to the total, so total plus equals to 1. Now we can calculate the accuracy. For that, we will now create a variable accuracy. We will take the total correctly guessed classes and we will divide it with the total testing size, so test data size. And then we can calculate the total validation loss by taking the total validation loss and dividing it with the index plus 1, and we can append now to the validation loss that total validation loss. Now I need to do the same for the training loss, so I will just copy it and paste it above here. I'll place a comment here, so validation, and here we'll paste it here, so the total train loss will be equal to the total train loss divided with the number of the batch, and then we will append to the training loss the total train loss, like this. And after these steps, we can now print out the epoch, so f-string epoch. Here I will print out the epoch, then for example the train loss, like this, and also the validation loss. And also we can print out the accuracy, so we will print out simply the accuracy, like this, and then simply train it. Okay, here we have an error, and I probably know that when we define the model here, I copied and pasted it here, so the input channels here will not be 1, it will be 6 from the previous one, and the output will be 16. Then the input to this here will be 16, and the output will be 120. So like this, and then again I need to run the model again, the optimizer, and then we can train our model. By looking here, we can see that our loss was dropping, and that it would drop even more if the number of iterations or the number of epochs was bigger. So the final accuracy was 0.87. We can also now plot the loss that we are saving, so plt.plot the training loss, and also plt.plot the testing or the validation loss. And then we can just do plt.legend so that we know what loss is what. And then this is the training and also the validation. Okay, and here we can see that the blue line is the training loss and that the orange line is the validation loss. And we can see that the loss was dropping and that it would drop even more if the number of iterations was bigger, as I mentioned earlier. Now we will also see one very interesting way of visualizing the model's performance. We will extract the test loader, one batch of the test loader, so test iter will be the iter of test loader, and we will extract the first batch, so images and labels will be the test iter.next. And then we will turn off the gradient calculation, so with torch.nograd we will now send our images and labels to the device that we're using, so images.toDevice, and also labels to and device. Then we will now make some predictions, so prediction will be model on those images. And this way now we have 64 predictions, so we will now extract those images numpy, because we want them to be in numpy arrays, so I_mean of the dimension 0, and also we will tell it to use the CPU for this, and also transform it to numpy arrays for I in images. This is a for loop, so this is the same as for I in images. Then I will be equal to I.mean dimension 0 CPU and numpy. These two commands are the same. So we'll stick with the first one, so I'll delete this. And now I will copy and paste the class names. You can find this data online. So these are the classes. And then we will iterate through 50 images, so for I in range of 50. And we will plot them with their corresponding label, and we will also color the label in blue if our model guessed correct, and in red if it failed predicting that class. Now we can check out the shape of this pred variable, so pred.shape. So we have 64 predictions with 10 elements in each of those. So now we can get the images. We will extract images, so images numpy will be a list of I_mean dimension 0. We will send it to CPU, and also numpy array for I in images. So this is the same as a for loop, just shortened. And now we'll create a class names variable, so class names, and in which we will store a list of class names. So I'll copy and paste them here. I have found this data online, like this. So here, simply, I created a figure, I iterated through 50 images, created subplots for those 50 images, I am showing them here, and then here I am asking, using a simple if statement, if the labels of I is the same as the maximum value from those probabilities, then the class name, I will color it as blue, and if it is not, then I will color it as red. So here we can see that the most of the items the model got correct, and some of them it got wrong, like the t-shirt, pullover, and also this t-shirt here. And that would be all for this tutorial. If you like this video, drop a like and subscribe to our channel. And I will leave a link for the blog post about LeNet 5, and also I will leave a link for the Colab code, where you can download the code that I was showing in this tutorial and you can work on the LeNet 5 model yourself. Thank you for watching and be safe.